So we start a new chapter and we want to talk about a very important aspects in advanced algebra, which being used in computer science quite frequently, and it is introduction to singular value decomposition, or known as SVD. And we have spent a bit of time, we see a little bit of applications of SVD where we want to use it, we see the theorems, and when you see the properties, then you will understand that why it is very useful in many computer science applications. Let's start by a definition of a positive definite and semi-positive definite. This you might have it from the undergraduate before. Matrix A is called positive definite or semi-positive definite if. Do you remember what was the definition of it? X transpose AX is greater than 0 for all x's belonging to Rn and a's belonging to R n by n. If this is true, then we call them a matrix to be semi-positive or positive definite. Now, singular values. We want to do something which is called singular value decomposition. So let's see what are the singular values. The singular value of matrix A, singular values of matrix A are equal to a square root of eigenvalues of A transpose A. You might remember how to calculate or obtain the eigenvalues from undergraduate level math. However, we will get back to this eigenvalue, the properties that it has, again in this course, maybe in 2 or 3 chapters afterwards. But keep this one in your mind. When we mean the singular value is just a square root of the eigenvalue. So if you know the eigenvalue, find this square root and you get the singular value. But let's start by giving a theorem and introducing our SVD. Let A belongs to R n by n with the rank R, then there exist orthogonal matrices U, which is belonging to R n by m, and V, which is belonging to R n by n, such that we can write A to be U multiplied by sigma multiplied by V transpose, where sigma is equal to, it's a matrix, it's a block matrix, which is in this form. So block matrix means that S is a matrix, zeros are vectors, or it can be numbers. And write the continuation here. And S is a diagonal matrix whose diagonal elements are sigma 1 up to sigma r belonging to r by r, and sigma 1 is, sigmas are sorted, like sigma 1 is the biggest, sigma r is the smallest, where sigma I is the i's singular value of A. In other words, we can decompose A into two orthogonal matrices, U and V, and a matrix, this is called singular values matrix. It's a matrix that on its main diagonal we have the singular values which are sorted. In other words, the first one is the biggest one, the second one is the second biggest one, and the last one is the smallest one. But we understand that this one, this matrix, which is n by n and has the rank r, will be decomposed in this form. S, whose size is r by r, and then this one is m minus 1, minus r, right? It should complete the number of columns. So it will be n minus r, its column. And this one should complete the row, so it will be m minus r, right? What we try to say is, inside the sigma, there is one diagonal matrix, one diagonal block, who looks like this. And it's a square matrix. And everything else is 0. But sigma is called a singular value matrix. Now, what is sigma 1? Sigma 1 is the maximum in value under a square root, right? Because sigmas are a square root of eigenvalues. So sigma r is the minimum eigenvalue under a square root. Remember, SVD will give us already the sorted sigmas. So if I give you that sigma I and sigma I plus 1, which one is bigger? Sigma I is greater or equal than sigma I plus 1. Which is very good, because it's good to know that they are sorted. Having the sigmas to be sorted, having u and v to be orthogonal, will actually makes us to, when we have the singular value decomposition, this is called singular value decomposition, have lots of properties assigned to it. We can extract lots of information through that one. That's why it makes SVD to be very cool. From a computational complexity point of view, SVD is expensive operation, but sometimes the amount of the information it provides is just too good that, and so cool that we prefer to use the singular value decomposition.
Is square root of something?
Sorry?
You put right there.
Square root of lambda max. You know that lambda means the eigenvalue. Lambda means in value. This is the general notation that we use for eigenvalues. So A is m by n, U is m by m, V is n by n. So sigma is the same size as the matrix itself is. U is called hanger, V is called Anhänger matrix. More specifically, we have A is U1, U2, so we can divide it into two block matrices. S V1 transpose V2 transpose. You may see that some books use this notation in here. Instead of this, they write V1 V2 transpose, which, if we do the multiplication, it means that we are having U1 as V1 transpose, because U2 will be multiplied by the 0 parts, V2 will be also multiplied by the 0 parts of our block matrix. So let's see what are U1 and V1, where U1 belongs to U2 belongs to V1 belongs to, and V2 belongs to. Where is V1 belongs to? Or let's go in this form. What is the size of S? It's R by R, right? What about the U1? U1, we know that because the multiplication should happen, it should be R, but what by R? It was already, this is already m by m. So it is m by R. And the rest are in here. So it's m by m minus R. Correct? And for the V1, again, we know that V1 without the transpose, it means that it should have R columns, because the transport makes this R to come to the row part, so we have the multiplication. And this in general is n by n, so it is n by R. And the rest are in V2, so it is n by n minus R. What is R? What is this R?
The rank.
It's a rank of the matrix. It's the rank of the matrix. So this means that S is a full rank matrix, right? It's a full rank matrix. The rank of a matrix is equal to, now look at here for a second. R is the rank of the matrix, which is the size of S. And what is S?
Square matrix with singular value.
It's a square matrix, it's a S-square diagonal matrix whose elements are
The square root of the eigenvalues.
whose elements are, there is one missing word between what you said and what I said, they're very equal. Whose elements are singular values, but there is one word missing. Whose elements are, look, we write the sigma in general, the singular value matrix, as S0, 0, 0.
Diagonal.
Yes?
Square root of the eigenvalues.
Forget about that, it's called singular values. So what is about S? The elements of S are something singular values. What is about these singular values? They should have some very small property, very important property in order to be in S, otherwise they cannot be in S. If they cannot be in S, where can they be? If there are some singular values, which I tell them that no, you cannot be in S, where else can I put them inside the sigma? Look, sigma is a matrix of singular value. If I cannot put some singular value inside S, where else can I put it? How many positions do I have inside sigma?
S is about
How many positions do I have inside the sigma?
4.
4 positions. If I cannot put it in S, where else can I put it?
0.
In zeros. So in order for them to be in 0, they have to be in order for singular values to be put in 0, they have to be 0. Otherwise I cannot put them in 0. In other words, S is a diagonal matrix whose elements are non-zero singular values. Non-zero singular values. What is the size of S?
R by
R
R.
by R. And S has non-zero singular values. So can you tell me that what is the rank of a matrix? The rank of matrix, which was R, which is the size of S, which S is the non-zero singular value matrices. So can you link them and make one sentence? Size of S tells us what is the rank, right? And we know that S has non-zero singular values. So by using these two, can you just put these two sentences together and make one sentence which says rank of a matrix is equal to?
The number of singular values.
Number of non-zero singular values.
Zeros.
Rank of a matrix is equal to number of non-zero singular values. Because if they are 0, look, if S was like this, sigma 1, 0, 0, 0, 0, sigma 2, 0, 0, 0, 0, sigma 3, 0, 0, 0, 0, sigma 4, if this was S, and if I tell you that sigma 4 is already 0, then you can say that this is S. Right? And then you say that, look, this is my one of the zeros, this is the other zero, and this is 0.
So it's possible to have a 0 as a,
Yes.
because the square root of eigenvalues possibly cannot give you 0.
No, the S square root of eigenvalue can give you 0 if the eigenvalue is 0. I mean, till now it was like that. I mean, from now on, I don't know if there is a change. Eigenvalues cannot be negative. They are non-negative, which means that 0 is included. Now, having, okay, finish writing the line. Tell you another challenge. You know that in general for the exam you are responsible for what I teach you in the class. And what I teach you in the class is more than what we have in the book. There are many theorems, many things that I am providing you in the class and they are not in the book, but in general you are responsible for them. One of those things is what I want to talk right now.
Yeah, there's many things that are not in the book.
But they're here.
Yes.
Good. So we can write our own book. And there are some chapters, especially when we start to go to the linear systems and linear equations, you will see that they are in the book and I say that you are not responsible for them. Now, as the singular values that we have in a singular value matrix, the elements of main diagonal, which are the singular values, are sorted. In other words, if I am in sigma 1, I am so sure there is no bigger number than sigma 1 inside this matrix. Then, or if I'm on the last element, I'm sure that there is no smaller value, non-zero value inside the matrix. Then it means that this has a good potential of giving us some information. Now, before that, let's define two terms. Have you heard of the term, this system of equation is a well-conditioned system of equation. Or this system of condition is an ill-conditioned system of equation. Or have you heard that in the signal systems, in control systems, that the system that we have is a well-conditioned system? Or the condition is ill-conditioned system. Maybe you have heard it in this form. The system is a stable system. The system is an unstable system. So let's see what it means from a mathematical point of view and then see how we can get to the singular value to define if an equation is a well-conditioned or ill-conditioned system of equation. If in a system of equations very small changes in the input is resulting in almost an unchanged output, then the system of equations is called well-conditioned system. Otherwise, it is called ill-conditioned system. In other words, for ill-conditioned, if we change the input very minor, like the input value instead of being 5, it is 5.001, we see that suddenly the output are significantly changed. Now, in the control system, maybe you had this example. Did you take the control system from Runiu?
Yeah.
Okay, maybe he gave you this example that we have a pyramid and we put the pyramid on its base. And then this is the output. And if I hit it, what will happen? It won't change. I mean, it will stay like this. Or even if it is changing, it will get back to what it was. So it's stable. It's the most stable design in the world, right? But if I put the pyramid upside down on its other end, and if I give a very small input, what will happen? It will collapse. So it's very unstable, right? It's called conditionally stable. I am not saying that having this is bad, having this is good. Next semester, if you are taking this advanced automation, you will see that I will give you an example that ill-conditioned or conditionally stable is actually used in the daily life. For example, the fighters, the aeroplanes which are used for the fighting, they always put their condition in the conditionally stable. That's why that suddenly they can drop their height, or suddenly they can increase their height. Whereas in the passengers ones, like in the Airbus, you cannot do it. They are much more stable. Okay? But, so we have this definition. Let's see if I give you a system of equation, how you can understand this is a well condition or a bad ill condition. One way is definitely through an example. You can give the values to the system, see what is the output. Then you can change them a little bit and give the value and then see how the output changes, which is very time consuming. Whereas singular value decomposition can help us in order to have a more systematic approach. It helps us to calculate something which is called condition number. For a matrix, A m by n, the ratio of the biggest singular value over the smallest one is called condition number. So kappa is, can you tell me that what is the biggest singular value? Sigma? 1. What is the smallest one? Sigma r. Where r is the rank. We know that the last one is sigma r because the rank is the number of non-zero signal values. And this is actually, we will talk about it towards this chapter, that sigma 1 is norm of A. Sigma 1 is norm of A. Can you tell me that what is sigma r? Sigma 1 is the norm of A. What can we say about an equivalent to sigma r? If S is this, what is S inverse? It's again diagonal, whose elements are just 1 over the values. So can you tell me that what is this one?
1 over sigma 1.
1 over sigma 1, 1 over sigma whatever. Which is, I write it as, right?
Yeah.
Now, if I want to represent this one with a norm, what can it be? Can you tell me that in here, what is the biggest number?
Inverse of sigma r.
This is the biggest number. So in other words, if we were sorting this, this could be a singular value matrix, this is one, of which matrix?
A inverse.
Exactly. This is the, well, not this one. 1 over sigma r is actually the biggest singular value that A inverse will have. So this is equal to this term as well. Sigma 1 equal to norm of sigma, we will prove it much later in this chapter. And one thing is that the kappa is always greater than 1. Is always greater than 1. Why? Because sigma 1 is always greater or equal than sigma r. So we have a condition number which is sigma 1 over sigma r, and let's see that how this condition number, well, what the condition number indicates and how we can use the condition number to relate it with the well condition and ill condition. The condition number indicates how much the output value of the operation or function or system can change for a small change in the input arguments. If kappa is small, then A is a well conditioned, in other words, the column vectors of A are well linearly independent if kappa is large, then A is an ill condition. In other words, the columns of A are close to be linearly dependent and A is about to be singular. Which means that with high probability, if we want to calculate A inverse, there is very high probability of finding lots of errors.